Yesterday we started our introduction to integrals by talking about area. And we saw that an integral really is just an area under a curve. And we discussed some ways to approximate that area using rectangles. Today's video, you're going to see how to use LRAM, MRAM, and RRAM to estimate totals in real-world situations. Let's start with a quick recap of what you should know already. You should know the big idea behind integrals is that an integral represents the area under a curve. If you want to be specific, it's the area maybe between two values, but we'll also talk more generally. You should know what LRAM, MRAM, and RRAM are, both in terms of a picture of them and in terms of what you actually need to do to calculate each one. And then in class, we also had this final realization, which is if your original function is increasing, the left-hand approximation is going to be an underestimate and the right-hand approximation is going to be an overestimate. And that's because an increased function is higher on the right than on the left. If the function's decreasing, we would say the opposite. A decreasing function is higher on the left than on the right, which means the left-hand approximation is an overestimate, the right-hand's an underestimate. Let's build on this idea of estimates. Essentially, a rectangular approximation is just an approximation. So it's worth talking about how good those approximations are. Look at the three images on the screen. Out of these three graphs, they're all the same parabola. Which of these three rectangular approximations is most accurate? Right, the first one is. And one way to articulate why is that the shaded rectangular area in red comes closest to filling up the entire parabola. The gaps are smaller than, for example, the gaps here, which is actually the worst approximation. And that's because there's so much space in between the line and the actual rectangles. So take a step back and see if you can identify why this is the best approximation and this is the worst. What can you conclude about n? Right, I would have said something like the higher the n, the better the approximation. If we use more rectangles, the shape of the rectangles comes closer to the actual area under the curve. Okay, so this is a huge realization actually. We spent all this time worrying about left hand versus right hand versus midpoint. The truth is, what affects your accuracy most is just the number of intervals. So let's take another look at the problem from yesterday. If you remember, we looked at this weird function e to the sine x, and we actually computed the area under the curve using 4 intervals. And this is the work for the left-hand approximation. We did the midpoint and the right-hand in class. And we came up with an area of 22.833, approximate area. This was with 4 intervals. I wonder how much the area would change if we used 5 intervals, or 10, or 50, or 100. Now, there's an obvious impracticality. Nobody here wants to go measuring 50 numbers and multiplying 50 times, much less 100 times. And this is where there's good news, because we're actually going to use technology to do this. If you will, in a separate tab, open up the link on the side of the screen, and it should lead you to a Desmos function setup that I made. It'll look something like this. If you are watching this video on a phone and you're unable to open, you can just follow along with the work that I do on the screen here, but you should plan to come to school early or to stop by at lunch so that you can play around with this yourself, so that you are going to be able to do it on your problem set. Ultimately, this is the technology you're going to want to use. Okay, so what are we trying to do here? We're trying to estimate the area under this same curve, and we're actually going to estimate it a total of 12 times. You might want to set up a table, something like this. For each of these n values, 5, 10, 50, and 100, we're going to estimate the left-hand area, or the left-hand approximation of the area, the midpoint approximation, and the right-hand approximation. Luckily, these numbers are just going to come from the program. So here's how you use the program. I'm going to calculate this first one to model for you, and then I'm going to ask you to do some of these other ones. So we're trying to get the left-hand approximation for n equals 5, and then just keep in mind this is your function, and this is the interval that we want. So if you have that Desmos page open, the first thing you're going to want to do is to set up your function. So click the folder here and it opens up what you need to do, starting with typing in the function. The function that we're interested in is e raised to the sine of x. And you can see the functions start to appear over here. Now, a and b are going to represent the beginning and the end of the interval. For us, we want our interval to start at positive 2, so just slide it over to 2. And we want our interval to end at 8. And then you want to make sure that we can see the correct area. So right now I can see the function. If you click on this circle right here, the area in question will appear. So I can't see the whole area, which means I'm going to zoom out slightly. You could also use these buttons or just scroll. And I'm going to adjust to make sure that I'm in a kind of convenient position to see. I can now see the whole area. This is what we're trying to calculate. And I'm actually going to take off that shading because we're going to want to draw rectangles in a second. I've just set up my approximation, and I'm going to go ahead and close this folder. Next, what we get to do is we get to choose the number of intervals we're going to want. For the first calculation, I just want 5 intervals. So I'm going to set n to 5. Oop, that's 5. And then I'm going to calculate the left-hand rectangular approximation. So I'm going to go to this folder, open it up, and follow the instructions. First, I click on this circle, and doing so, the green rectangles appear, and I can just double check that there are 5 of them. And they are left-hand approximations because the left edge touches the curve. And then actually, it tells me the numerical value of this approximation right here in the bottom, 7.179. And I'm just going to go ahead and record that in my table, 7.179. We'll repeat this same process for n equals 10. And in fact, it's very easy to do so just by increasing it to 10. And as you do so, you can see the number of rectangles change. And our approximation changes a little bit as well. So for n equals 10, we get 7.175. And then if we continue for n equals 50, you notice that the rectangles are so small we almost can't see them. Although if you zoom in, you will still see that we are still overestimating on this side and underestimating on this side. When we go to our actual numerical value, it now looks like 7.206. And finally, for 100, which is the most rectangles you're allowed with this tool, notice how smoothly the rectangles come close to approximating the area. And we end up with 7.212. So looking at the table of values that you've just recorded, what can we say about the accuracy of my approximation as n gets larger? Exactly, we would say that the accuracy increases. So if I had to estimate, the best estimate so far would be 7.212. I want you to go ahead and do the same process for MRAM and RRAM. Again, you're just using this tool to visualize and then to ultimately just get the numerical answer. You don't need to worry about what these formatting looks like. It's just an easy way for you to add all these numbers up that I've computed. In order to go back and do RRAM and LRAM, you're going to want to reset n to whatever original number you wanted. And make sure that you take away the shading, because the green shading was just for LRAM. So click that circle to turn the left-hand approximation off. And then you can go into the midpoint approximation and turn this one on. You should be good from here. Remember, you've already set up your function. Go ahead and calculate the rest of these values, all 8 of them. When you hit play, I'll show you what I got. These are the values that I calculated. Notice that they're all approaching the same number, even though they start off from different directions. And looking at the table of values here, since we know that the higher n, the more accurate the approximation, there's a couple conclusions we can draw. First, we can say the area under the curve is approximately 7.22 units squared. And we can also conclude that as long as we use a high enough n value, it doesn't really matter which approximation we use. They're all going to get pretty close in the end. Okay, now that you're comfortable with the technology, don't lose the calculator. You're going to want to use this again and again. For different functions, you just go to Setup and put a different function in, change your values to use this. But let's move on to the real point here. Remember, we were supposed to be talking about integrals in the real world. So let's talk about the example that I use as the background page for this unit. In that picture, there was a waterfall and then a little graph. The graph is showing you the rate of the water flowing over that waterfall over time. So what does that mean about the height of this green line? If this is the curve, what does the function's height represent? Exactly, it represents a rate, or you might say a derivative, but it's the rate of how much water is flowing into the pond. If that's what the height of each of these rectangles represents, or the function represents, and suppose that each of these little rectangles is 1 minute long, the x-axis, this is 1 minute's time, what would the area in this rectangle really tell us? Yeah, we would be multiplying time, 1 minute, times speed of the water coming in, kind of like distance times time. It tells you the total amount of water that goes over the waterfall and into the pond in the first minute. And so then this second rectangle, the area of this rectangle would tell you the total amount of water that pours into the pond during the second minute. And this area would be the amount of water flowing into the pond during the third minute and the fourth minute, so on and so forth. So if we add all of these areas up, what do we end up with? Yeah, we end up with the total amount of water that flowed into the pond during all of these minutes. Over the course of the 12 minutes, how much did the water in the pond change? Notice that that's no longer a rate. The y values of the function are a rate. The area under the curve is a total amount, not a rate. To put it differently, this is the example that you saw in the Techno video that I really liked. In this example, the curve was the derivative function, the velocity, the shape of it. And at any given time, the height of that curve represented speed, which is a rate. But when we calculated the area in total, and they showed you by taking these chunks of area down here to the original graph, the area under the curve turned out to be the total distance, which is the total change in the original function. This is fundamentally the meaning of an integral. If you're looking at a graph, this is the most important thing from this half of the video. If you're looking at a graph of a derivative, the area under that curve represents the total amount in whatever the original function was, the function whose derivative you're now looking at. Let's test this. On the screen, there are 4 different scenarios. Read each of these scenarios and tell me which ones are going to require you to calculate a derivative, which ones are going to require you to calculate an integral, and which ones are you going to use neither, maybe. Remember, a derivative is when you're looking for a rate of something. An integral is when you're looking for a total amount and you're given a rate. See how you can do. That's right, A would be an integral situation because we're given a function that's a rate. We're told how much someone earned. Think about the units. Earning is like dollars per year. It's a rate. We're given a rate function and we're asked to find a total amount. How about B? Yeah, this is a derivative. This is the opposite. Here we're given a function for tells you how much of something there is. And it is each month, but that's not the amount of money you get each month. It's just you have a certain amount of money the first month, a different amount of money the second month. Notice that that's not a rate. It's not about something's changing. It's just the amount you have over time. And what we're asked to calculate is a rate. So in this case, we're calculating a derivative. Read these first 2 examples again. It's really key that you understand in the meaning of the problem why this one's an integral and this one's a derivative. Do the last 2 real quick. Awesome. C's a little tricky because we are actually given a rate function. How fast it's traveling is a rate function. But instead of asking for the total distance, which would be an integral situation, we're asked for when it slows down, which is actually asking about acceleration, which is the derivative of velocity. So we use a derivative here. This last one is